Hey everybody! Today we wrapped up our study of momentum, but we actually wrapped up our study of a particular kind of momentum. This momentum is known as linear momentum. It's momentum that's associated with objects moving from one place to another. But that's not the only way that an object can move. Objects are also able to rotate. And so there is a similar concept known as angular momentum. It's just the momentum that an object has because it's rotating. One of the nice things about angular momentum is that you can think about it much like linear momentum. It's just that instead of talking about objects moving from one place to another, you're talking about them rotating. So for example, if we have an object with a certain amount of momentum, we change its momentum by applying a force. For angular momentum, it's the same idea, except instead of a force, we have what's known as a torque. A torque is equal to a force times a distance. But the distance from what? To see that, let's look at this door. What are we doing if we want to open this door? Well, the door has hinges on this side, and when we push on the door, we are rotating the door around its hinges. Torque depends on two things: how hard we're pushing on the door and how far away from the hinges we're pushing. The farther away we push from the hinges, the larger the torque, and therefore the larger the change in the angular momentum of the door. To open this door, it's easiest to just push on the outer edge, like so. It's fairly easy to push the door open in that case. This is because my hand is pushing on the door quite some distance away from the hinges, and so the torque is rather large. But what happens if I do the same exact thing, except try to push on the door here instead? I have to push extremely hard to get the door to open. Why is this? Well, it's because the force is now being applied very close to the hinges. Because the distance between the hinges and my hand is smaller, the force I must push with in order to make the same torque is much greater. The amount of torque that I need to provide in order to push the door open depends on the door itself. Things like how heavy it is, how big it is, and so forth. Moving my hand from here to here doesn't change the amount of torque required to move the door. However, it does change the amount of torque that I'm able to provide. Because the distance between the hinge and my hand is less, the force I must provide in order to provide the same torque is much greater, and so I have to push much harder on the door. For one more example, let's consider this wheel. The door was not able to rotate a full rotation because there's a wall in the way. But this wheel can rotate as much as it wants. If I push on the outer rim of this wheel, it starts spinning. I didn't have to push very hard to get the wheel to do this. But what happens if I try to push on the very inside of the wheel? Well, I can still get it to spin, but I must provide a much stronger force to get the same result. The reason is the same reason as for the door. The amount of torque I must provide to get the wheel to spin depends on the properties of the wheel itself, its mass, its shape, and so forth. But the amount of torque I'm providing does depend on how close to the center of the wheel I am pushing. If I'm providing a force on the very outer edge of the wheel, it provides a much greater torque than the same amount of force applied at the very center of the wheel. Just as with momentum, torques have direction. But what direction is this wheel traveling? I mean, it's not really traveling in a direction at all. It's just rotating. So how do we assign a direction to this kind of momentum? There's a convention that we use for this. It's called the right-hand rule. Let's say that the wheel is spinning this way. The right-hand rule says that if we curl our fingers in the direction that the object is rotating, then our thumb points in the direction of the torque. There's nothing particularly special about this choice. There's no reason that it couldn't be a left-hand rule. The right-hand rule is just a convention. The right-hand rule tells us two things. First, if we have an object that's rotating, its angular momentum points in the direction given by the right-hand rule. This wheel is rotating like this, so we curl our fingers in that direction and our thumb points to the left. The right-hand rule also tells us the direction of a given torque. We do it in the same way as with angular momentum. If I was providing a torque on the wheel that was going to cause the wheel to spin this way, then the direction of my torque would be in this direction, just as the angular momentum of the wheel was in this direction. Just as with momentum and forces, it's totally possible to have torques that are pointing in the opposite direction of angular momentum. We'll see in a little bit how we can use this information to solve some interesting problems.